Good morning. My name is Kosta Ilic. I've been with National Instruments for about 30 years. The first 20 years, I was working in product R&D, building an assortment of products, hardware products, working as a driver developer, working on software programs. And then I moved into professional services organization where I wanted to learn how the products that I used to develop are used in real systems to test things. And I stayed there for just under 10 years. About 3 years ago, I moved into transportation BU, where I now work on system design. So for the past 10 years, I've been working on test system development. And that's why I'm here and doing this presentation. Before I begin, I'd like to ask you, how many of you have background in electronics or electrical engineering? Very good. How many of you have background in software development? Very good, thank you. How many of you have background in mechanical engineering? Quite a few. How many of you are lawyers? Nobody. Very good. Okay, one. So I have a picture here. How many of you think that this is a test system? Few people? How many of you would feel comfortable testing things with this thing? Okay, not very many. How many of you would feel comfortable giving this to an operator on a production test floor to test your product with? Nobody. Very good. Okay. I wanted to get this messy picture of equipment, and I'm going to argue that this is a collection of equipment and that this is not a test system. I know people who are very effective with this, but it's because that's their collection of tools and they can manage it, and I can manage a similar collection of tools myself if need be, but test system, this is not. Okay, want to get into a little bit of a definitional phase here, and I pulled a couple of definitions. The first is definition of a system in general, and it's an arrangement of parts or elements that together exhibit behavior or meaning that the individual constituents do not. And so this is a very general the definition of a system, and this can be a technical system, it can be a non-technical system, it can be a legal system, it can be an ecosystem. It can be made by people or not made by people. When you get into engineered system, the definition is that it's a system designed or adapted to interact with an anticipated operational environment to achieve one or more intended purposes while complying with applicable constraints. It's a mouthful, but it's a definition that I pulled from a respected source. And I think that it's fair. I will not attempt to define a test system. I will argue that a test system is always going to be an engineered system. Chances are that it's designed to test some dots and within constraints and do some other things and so on. I would like to try to describe a test system in a bit of a context. And the context that I'm going to use is that of a test station or a test cell or part of a production line where you're doing the test. And I will isolate a test system as a portion with some equipment. I will talk about dots, and then there is very often a test fixture that goes between the test system and the dots. And this split between test system and the rest of the station is useful. Sometimes you can connect dots directly to the test system, but in a large number of cases you can't. And one of the advantages is that separating it like this makes it possible for you to test more than one type of dot with the same test system. If you have a family of dots or evolution of a dot and there are some changes in connectivity and mechanical shape and whatnot, you can make that with a test fixture that you adapt to the dot and to the test system as well. Okay. We're going the wrong way. What is a rake? Okay, I pulled the definitions of the rake and the cabinet from the industry standard for rakes. For purposes of this presentation, I will take a little bit looser definition, and I will use the word rake to refer to a freestanding and self-supporting structure for mounting test equipment, regardless of whether it's an open structure or an enclosure, and regardless of conformance to this fine industry standard. Because the principles will apply whether you're following that rake standard or not, if you're mounting test equipment in a frame of some sort or an enclosure of some sort. What is the value of having a rake system? At one level, it's easier to manage equipment when it's all mounted neatly in a rake than when it's set up, as I showed on the picture earlier, on a random desk. And so you're managing one big piece of equipment instead of managing a whole bunch of little pieces of equipment. If you have a need for multiples of these things, you get better footprint because everything is neatly arranged vertically and you can take several square feet or square meter of floor space as opposed to taking a whole lot of desk space. You can get simplified interfaces to the test system, whether they're electromechanical interfaces in terms of connectivity to the fixturing and the dots, or user interfaces in terms of software and other mechanical interfaces that may exist on the test system for the operator to perform their task, if there is an operator involved in the test cell. So we could talk about best practices for a long time, and I'm sure there are plenty of best practices that will be particular to the kinds of systems that you're working with, types of dots and environments that you're operating in. We will not be able to cover everything. I will go through a selection of best practices here. So the first thing I want to mention is you need to know what the requirements are. And this is fairly basic at some level. On the other hand, I have found myself in meeting after meeting where engineers love to talk about solutions. And every once in a while, I have to interrupt the conversation and say, well, what is the problem that you're trying to solve? Because without understanding the problem, I can never evaluate whether the solution is brilliant or not. And it's not easy to get requirements. You may have a client and they may think that they're describing their requirement, and then when you deliver the final thing, they're not happy. And so it's very, very difficult to get requirements right. And part of the challenge is that people who are producing those requirements may or may not be able to verbalize what it is that they're looking for. You may be fortunate to work in a place where you will get a wonderfully written requirements document, and that's great. It may, in fact, be really good. You may be working in a place where someone is telling you a story and you're trying to capture the requirements that way. But whatever the case is, this is really important. If you follow every other practice right and you miss on requirements, the thing will not be successful. The next thing, you need to understand the context where the test system will fit. And when people visit with me and start talking about a new test system, they almost always talk about the dots because that's kind of intuitive. But the next question that I like to ask is, okay, so what is the fixturing going to look like? And sometimes they know and they can tell you a whole lot about it, and sometimes they don't know, and it's like, well, that's a problem that needs to be resolved. And then you can keep asking more questions. Is a human going to be moving dots in and out of the system? Is a machine going to be moving them in and out of the system? And then a whole lot of decisions depend on that. So understand the requirements at one level, understand the context at the next level. The next thing, constraints. Two test systems shown on the slide. How many of you, all things being equal, would prefer to buy the system on the left? Nobody. Okay, I would not buy system on the left for work because I would get in trouble with my chain of command. They would get me in trouble. And I think that the response from the room is confirming that. You may look at the thing on the left and say, well, this is goofy, but you can also think, well, maybe this is just a cosmetic difference, who cares? It turns out that it's more than the cosmetic difference. If you look at Let's see. If you look at this thing, this is an emergency shut-off button. Look how visible it is here. Not so much there. It blends in with the camouflage colors. So it's more than a cosmetic issue. And you may be looking at this and thinking, well, Costa, you're exaggerating with this slide. And I am. However, I have been in a situation where a project manager on an adjacent project got feedback that the shade of gray that was picked for their test system was off. So it's not that the color in general was wrong, it's the shade of gray wasn't right. So silly as this slide is, there may in fact be a constraint that is important to someone, and it may be as simple in a sense as a shade of gray, but changing the shade of gray on paint may be really difficult to pull off late in the project if you weren't aware of it from the get-go. So a bit silly, but be aware of the constraints. Requirements, context, constraints, and knowing when you're done. So if you got the first three things right, why do you bring this up? Because when you talk with people about requirements, they will tend to talk about test this, measure that, do this, do that, do the other. And then when you think that you're done, they may say, oh, you need to go and comply with these requirements for commissioning a test system. And I bring this up because it's good to know this up front, and then you can plan for it better. And you may work with someone who has a 100-page requirements document for commissioning a test system, and you have to prove this, that, and demonstrate the other, and this, and collect this data, and present it in this way. Or it may be a place where, well, when George tells you that you're done, you're done. I would pick a 100-page document any day of the week, but every once in a while you have to work in a place that doesn't have that level of maturity. Anyway, so this is something that I bring up as a separate thing. How do you know that you're done? There is a slew of additional considerations when you're putting together a test system. You have to worry about component selection. Any one of these topics I could talk about for about an hour, but we don't have that time. And then there are considerations about which software you want to use. And well, it may be a good idea to document the system. If you're the only person using the system, it's less important. But if you're building a system that'll ship to distributed locations across multiple continents, do you really want to get a call at 2 o'clock in the morning with someone asking you how to hook this to that or the other? And then somebody will need to put the system together. If you're doing it, that may be simple, but if somebody else is responsible for putting it together, you need to have a plan for manufacturing the system. And bring up and repair. It'll break. How is it going to get fixed? And maybe you want to have preventative maintenance. And presumably there is calibratable equipment in there. How is it going to get calibrated? And somebody will operate it. If it's not all automated, how are people operating the thing going to be trained? And this is just a sample of things to worry about. It's a complex problem. Do any of you want to bring up any other considerations that you take into account when you put together a test system? No? Yeah.
Installation, location, and its requirements.
Installation, location, and its requirements. Very good. Where will this go? Do you have what the test system will need to function properly in the plane that you're going to put it in? Do you have the right kind of power supply? Is there something pneumatic? Do you need to have compressed air? If you need to have compressed air, what is the quality of that air going to be? How pure does it need to be? Are there temperature issues? Are there humidity issues? Do you need to have air conditioning in the room to put the test system in? Very good point, thank you. Anything else?
Safety.
Safety, yes. What are the safety considerations? Are you going to put together a test system that can harm someone? You don't want to do that. There will be more about that in a bit. Anything else?
Can you keep people from stealing parts off of it?
Can you keep people from stealing parts of the test system? I have not had to deal with that. I have worked with a team that had to figure out a way to keep rodents out of test systems. So you reminded me of a really strange environmental consideration. Want to bring up a thing that I have found useful in test systems that I have worked with, and it's maintenance software. And if you build this as part of the system, it can help you with manufacturing tests. And the first part of it is, are all the things that you specified to be in the system that you can detect through software in the system? And is anything else in there? And that's not a good thing. And so having maintenance software is something that I have found useful. And this is the first level of, are the right things in there that you can detect in software? The second part of it is, if you want to make sure that everything is connected right, and you don't have ability to establish that through software alone, and you want to go all the way to the electromechanical interface of the system, having fixturing that maintenance software can interact with to make sure that all the cables are in where you want them to be. And what I'm showing here is called FDT, Field Diagnostic Tester, for a system that Michael and I worked on. Staffing for success. It's a complex thing. We found all the considerations. A test team structure that I have found to be beneficial when putting a thing like this together is to have a program manager, to have a technical lead that is responsible for every technical aspect of the system across the disciplines involved in putting it together. That role is fairly difficult to fill, is what I found, because people tend to gravitate to what they know best. And you need to find someone who is curious, on one hand, willing to talk with a bunch of people on the other hand, and who doesn't mind offering their throat as a single throat to choke for anything technical in the project. And then you will need domain experts, especially if you're working with a kind of DOT that you're not familiar with. It's good to have someone who understands the DOT and all kinds of other things that may come into play, any environmental peculiarities, any other peculiarities that go on. Then you need test engineers, electrical engineers, and software engineers, some kind of mix of these three disciplines. Test engineers tend to be very, very versatile and may be able to do multiple kinds of things. Electrical engineers, software engineers, maybe in a different way. Mentioned documentation, good to have writers. Engineers can write really well. I take pride in being able to write documentation, but I have seen what excellent technical writers do with my documentation when I hand it to them, and what I get back tends to be a whole lot better. And this is a team composition that you need for a test system, no matter what kind of test system you make, whether it's reg-based or not. But when you're putting together a reg-based test system, you need to have mechanical engineering talent on the team to make sure that things work out well. And to illustrate this with a personal experience, I had a project where I needed to use an off-the-shelf reg and make an adaptation. And it was an internal NI supplier of instrumentation that knew exactly what I was doing, and what came as a list of requirements for me from them was, you can use the equipment that we're giving you in this reg, but you need to replace the 4 feet. There were legs that were 1.5 inches tall. You need to lift it to 2 inches, and you need to block air from circulating on one of the 4 sides at the bottom of the reg. And so I'm looking at this. The reason for that blocking is cold air inlet was on the back of the system, and hot air was coming from the bottom. And so we didn't want to have hot air coming into the cold air inlet here. So requirements there: geometry, middle school geometry, great. I can relate to this. We were in a bit of a rush, and I had a mechanical engineer part-time assigned to the project, and I asked him to do something quickly, and he came up with what is shown on the left. And it met all of the requirements. And then the program manager came in and looked at it and said, well, this will do to get us going, but it looks like you went to a big box hardware store and bought a piece of aluminum and applied a saw and a drill for screw holes. And that just looks ugly and unacceptable. Our logo is on that test system. Do something better than this. Mechanical engineer, so I didn't argue with the PM because I thought that he was right. And I went to the mechanical engineer and asked for help. And he designed something that we reviewed and rejected. And then he came up with a third design that we reviewed and rejected again. And then he came up with this piece of synthetic material that was leveraging the legs that we had to begin with. So reusing some equipment there. And when you look at this, it looks like it belongs and it was meant to work that way. Oh, and that sticker there, that could be a whole presentation in and of itself, that safety sticker. So it turned out that it's not only a cosmetic issue, there is a safety thing. And I like to bring this up because it was a relatively simple set of requirements, but without a mechanical engineer and all of his skills, I would not have been able to succeed on this project. And kind of a compliment that we got for the design on the left was when the team responsible for the next generation of this rake just stole this. Anyway, and with that, I will pass the presentation over to Michael, our mechanical engineer.
Thank you, Costa. As was hinted at, I am Michael Singerman. I'm a mechanical engineer working in systems R&D at NI, and I also work on rack-based test systems. So Costa's been talking about a lot of big picture considerations and execution for the system. I am choosing a few that I'm going to go on to a sort of technical deep dive and hopefully build a little bit of intuition for people who aren't familiar with these concepts. Starting out, though, another list of things to think about. I'm not going to go through all these things. There's a couple on here that I'll go into in more detail, but the point I want to make here is this is a big list of things, and you can't just go down this list saying, I met this, I met this, I met this, I met this. Designing with one or two of these things in mind might make two or three more worse than they would have been if you had chosen a different set of priorities. And that goes for these system level designs of what needs to go in there, how does it need to perform where it's deployed. And it also goes for how you choose what equipment needs to go into that system and be a member of that system. Everything needs to be able to work together and complement each other and fit together in a way that allows your system to meet all of its requirements. So yet another list that is too long to go through. But the four topics that I'm going to spend the most time on and go into detail on are these: mechanical stability, serviceability, thermal design, and ergonomics. These are near and dear to my heart. They are some of the most important ones in my opinion, and I spend the most time on these. So I'm going to start with mechanical stability. This gets to the safety consideration. Depending on where your system is deployed, depending on who your customer is, depending on how it's going to be used, there are various specifications that may give you requirements and govern how stable your system needs to be. And that means something different when you're looking at different specifications. One that we use most frequently for our AT systems is IEC 61010-1. And that specification has two tests that we evaluate for all of our systems, and I'm going to talk about those tests. So the first one is a tilt test, where your system needs to be able to tilt at some angle, in this case, say 10 degrees, and not overbalance and continue to fall. So I've illustrated that beautifully here with my stick figure. You want that rack to stay upright. And I think a lot of people here probably have the intuition that this depends on the location of the center of gravity in the system. So I brought a graph along with me that shows the exact relationship to the stability of the system based on its location of the center of gravity. And this curve would look a little bit different at a different angle, but as long as your center of gravity is below this horizontal angled line, your system will be stable. And on the right side, or I guess, yes, the right side of this graph is going to be if the center of gravity is located right in the middle, right in between the wheels. And as you move the center of gravity over across the side of the rack towards one side that's being tilted, the center of gravity needs to move lower and lower in the rack in order for it to remain stable. A lot of people have intuition about this. People design and lay out racks to try and keep the center of gravity low all the time to pass this test. But there's another test that people don't have the same level of intuition about, and I was pretty excited to try and figure out the first time I encountered it, which is the No, I'm losing more. The tip test. So this is a test where the system needs to be able to withstand a sideways force, whether that's somebody leaning on the side of it, pushing on the top of it, maybe putting something heavy on a table that sticks out of it. And in this case, once again, the test depends on the location of the center of gravity, left and right, but it also depends on the overall weight of the test system. So I've plotted two curves here for two different test systems. As the test system gets taller, the amount of leverage you can apply to it at the top grows. So there's different curves for different heights and different locations that you might apply force to the test system. And again, on the right side of this chart is center of gravity in the middle. And as long as your rack is heavier than what this line is telling you it needs to be, as long as you're above that line, then your rack will remain stable. So moving to the left, as the center of gravity goes closer and closer to the edge of a rack, the amount of weight required to remain stable starts going up really, really quickly. And as soon as you're popping outside the side of the rack, then you can't get back. So one thing that's missing from this is the vertical height of the center of gravity off the ground. For this test, that doesn't actually matter. Only side to side and weight matter. And it turns out that in most system configurations for racks, this is the dominant test. So it is important to keep your center of gravity low, but it's also important to keep it centered and maintain the weight of your rack. Now, you can always make your rack heavier and try and get it above the line if the chosen arrangement of equipment in the rack has pushed the center of gravity off to one side, or there's a table on it or something. But we have to keep in mind that a rack can't hold an infinite amount of weight. If you have a 10,000 pound rack, it's going to be really hard to maneuver, really hard to use, might fall apart. But that brings me to my next topic, which is ergonomics. So the reason you're building a test system is so that someone can use it. And it's important to make sure that that person who's using it isn't going to get hurt and is going to be able to be comfortable and continue using the test system. So the person who's using this system most frequently is going to be the operator, kind of definitionally. And this person is interacting with the test system using the HMI human-machine interface. That might be keyboard and mouse. That might be a monitor. That might be, you can see lower down here, we have some DUTs and a DUT fixture on that tray. Those might be being changed out frequently. And that repetitive work can take a toll on somebody if it's not put in the right spot on the test system. There's a lot of information on how best to design a system for ergonomics. NASA has sheets and sheets and sheets of specifications that tell you exactly where someone can reach based on their height and how long their arms are. OSHA has guidance on everything from how far away from somebody a work surface should be to what angle of the neck is most comfortable for an operator to have. So we can see here in this picture, the monitor might be up above the operator's head, but they can tilt their neck back safely a few degrees without causing any strain over the long term. This test, the DUTs and the fixture are placed in a place where the repetitive action isn't going to hurt this person. And there's a trade-off here sometimes when you need to put your DUTs right in the middle of that rack, but there's another piece of equipment that wants to be there just as much. And you need to choose when to prioritize ergonomics over some other requirement of a piece of equipment. But the operator is not the only person using this test system. Before they ever get a chance to see it, you have to build it. And designing for manufacturing is another critical place where you have to make trade-offs in how equipment is arranged in the system. Depending on who's building it and what equipment they have available, they may or may not be able to take really heavy equipment and put it at the top of a tall rack. That is a difficult and dangerous thing to do for a person, so you may need a table to help out. It can be easier to put heavy equipment down at the bottom, which once again also has really nice synergy with the center of gravity problems we were talking about earlier. So that's one consideration. Some equipment just geometrically won't fit in the rack where you want to put it. You can't get it there. It might work that way in CAD in a model, but you just can't take it from outside of the rack and get it into the rack. So that's another thing to be mindful of when choosing equipment to place into a test system, because if you can't put it together, you can't get it to a customer, you're not going to be successful. Serviceability is another consideration. People are using this rack. People need to maintain the rack. If something breaks inside it, if something needs to be debugged, calibrated, if you need to lock it down so somebody doesn't walk off with a piece of equipment that's inside the rack, how exactly somebody is going to get inside the rack to maintain it is an important consideration. How much of the rack do you need to take off to get to a piece of equipment that needs to change? How frequently do some things need to be touched or other things need to be touched? Safety-wise, do you need to add lockout tagout to your power system so that if somebody's in there working, somebody else can't just flip it on and subject the first person to a hazardous voltage? All these things can be defined in your requirements. Sometimes you'll have a requirement like, I need any piece of equipment in the system to be reachable and replaceable in 5 minutes. And that's going to have a high impact on where things need to go, how densely packed your system can be in order to enable that to happen. And speaking of a densely packed system, I'm going to talk a little bit about my favorite subject, which is thermal requirements inside of a rack. So this is something a lot of people are aware of. Again, if there's hot things in a rack, you don't want things to be so hot that they don't work. There is a lot of nuance to exactly how to design for thermals, and oftentimes designing for thermals might come at the cost of another consideration or another optimization choice like ergonomics, like serviceability, like stability. So I've constructed an example to illustrate this concept, and I'll go through it, and hopefully this will be interesting. So I'm using two pieces of NI equipment. I'm sure everybody here is familiar with the PXI chassis. And I've got a side view diagram of this. For both of these pieces of equipment, the blue arrow is where cool intake air is coming in for the cooling. The yellow arrow is where hot exhaust air is going to leave the chassis. And then I've got a picture of a module showing, let's say, the serviceability side. For both of these, it's where the module could be swapped out or reconfigured. That's not the only definition of what serviceability is for these, but we'll use it as shorthand here. So I put these two pieces of equipment in a rack and did a thermal simulation to look at the airflow inside the rack. And that's what you see here. This is a side view of a rack. The background color in different shades of blue and green and a little bit of red and yellow is air speed in the rack, not temperature. I think air speed is going to tell the story a little more clearly than temperature would. At the bottom of the rack, on the right side, is the intake where the cool air is entering the rack. And at the top left, we've got fans. They're accelerating air really fast. You can see that's where the exhaust air is going to be going. There's 4 white boxes in the middle. The bottom 2 we can ignore. They're just taking up space. But we'll call this top box our PXI chassis, and the middle box the SLSC chassis. And right now, in this arrangement, they are optimized for thermals. Their cold air intakes are on the same side of the intake of the rack. That cool air can come right in the rack and go up into those cold air intakes of the chassis. You see there's a field of blue arrows superimposed on the background, and that's tracing the pass of air as it goes into the PXI chassis and the SLSC chassis, and a little bit out of the SLSC chassis as well, just kind of highlighting these paths. And we can see that this is a pretty clean story. All that air comes in, goes into the chassis, goes out. There's an interesting thing that you might notice at the top where this PXI chassis' top exhaust is coming back around and going right back inside. There's a lot of equipment with side-to-side airflow where that same thing can happen if there's 2 sides and a rear. It may or may not be a problem in your system, but it's something to be aware of and something that you can design to mitigate if you're concerned that might be a problem. But let's say that serviceability is a really critical component of this system. And I've optimized this for thermals at the expense of serviceability. You can see that in order to replace a PXI module, you have to open one side of the rack. But in order to replace an SLSC module, we have to open the other side. And if you need both, you've got to pull the whole rack out, and you need access to both sides of the rack. And that can be pretty onerous depending on where it's deployed. So let's see what happens if we turn that PXI chassis around and see what happens with the air. So here we have a system that's more optimized for serviceability at the expense of thermals. These blue arrows are way more chaotic than they were in the last system arrangement. They're coming all the way across the rack on the bottom before they have a path to go into the PXI chassis and into the SLSC chassis. That's really hard to understand and predict, and it's really hard to know what the consequences of that are, but suddenly this is much more complicated. It's more sensitive to the placement of all the other equipment in the rack than it was before. And it's pretty tough to see here, but all of the exhaust from the SLSC chassis, you can see this little yellow and green spot right there, all of that heated exhaust from SLSC is now getting sucked right into the intake of the PXI chassis, preheating it, and causing the temperatures in there to potentially be higher than they were in the last configuration. So it's really hard to know when you're choosing whether to optimize for serviceability, operability, or thermals, what's important and what the consequences on each of those other considerations are going to be when you're choosing to optimize one over the other. So this is just for point of comparison, a thermal optimized system and a serviceability optimized system. And I want to touch a little bit more on the question of how do I know when I need to think about thermals a lot? How do I know when to prioritize thermals over something else? Because it's very complicated and hard to know. So the quick back of the napkin calculations are, if there's something really hot in the system, if you can put that hot thing near the top of the system so that all of its exhaust heat is going out the top, if that's where the exhaust is, you might find yourself in less trouble than you would be if that has to go near the bottom of the system to ensure stability or operability or something else. If the total power dissipation of heat inside your system is several kilowatts, then you may need to consider thermals over other things. But if the duty cycle is really low, say all that heat's only on for 2 seconds everything in the system has a really high environmental rating, it can handle up to 85 Celsius or something, then maybe you don't have to worry about that as much. But if the duty cycle is really, really high, then all of the little effects of the airflow in the system can come back and haunt you. If you have a system that's chock full of instrumentation, that's piping power right out of the rack into some other equipment, maybe it's full of power supplies that are really efficient, then even though you're consuming a lot of electrical power, it might not be a challenging thermal problem because the heat's not staying there. And I wanted to call attention to one specific corner case that I've encountered, which is that a lot of test systems that are deployed have an uninterruptible power supply in them. And sometimes that power supply is keeping heat dissipating equipment in your test system on, but maybe it's not keeping the test system fans or other cooling apparatus on. So you can have what basically is an oven if that supply can stay on for a long time without also powering the cooling apparatus of the system. So it's important to carefully architect what you're preserving with a power supply if thermals is a major consideration for you. So hopping back over to my first kind of agenda slide, there's a lot of different things that you need to find a perfect balance for when you are designing a test system. Some of this is going to come from customer requirements. Some of this is going to come from the exigencies of how things just need to fit together in your system, or if something is really sensitive thermally and needs to be at exactly 25 Celsius to make its measurement, or if it's just not going to fit together and be usable by an operator. But ultimately, a successful test system needs to find the confluence of all of these different things where all of them are good enough to meet the need of a customer or the operator or whoever is ordering the system. So it can be really difficult to find this point. It's an iterative process. You need to understand what the use cases of the test system. You need to understand what the expectations, what the conditions of acceptability are. But with all that together, it can be really possible to find this happy medium and get where you need to be. With that, I'll open it up to questions. Okay, thank you, everybody.